A pleasure to introduce Gaurav Patil from the University of Toronto, and he will be speaking for us about, on number fields with fixed degree and bounded discriminants.
Thank you for this opportunity. Uh, yeah, I'd like to start with this. The question sort of begins at Hermit's theorem, what Hermit and Minkowski showed. So, Hermit showed that Hermit and Minkowski showed that the number of number fields with a bounded discriminant or any fixed discriminant actually is finite. Actually, Hermit showed this for 30 years before, but he talked about it in terms of polynomials and roots rather than number fields. This was before Didcot, and later on, Minkowski was able to give a sort of a slightly more effective bound to be more exact. So what Hermit actually showed was that number of number fields of a fixed discriminant is finite. And from here arises the question of how many are there, how many such fields are there. And so this is where the question starts, the question of how many are there, how many. So to that end, we set up this particular function that counts these number fields. Actually, to that end, there's a relevant theorem that of Minkowski that actually shows that this is, I think, attributed to Minkowski, Stark, and Odlyzko. And they show that the number of that there exists a constant, absolute constant c greater than 1, such that discriminant of a number field is actually greater than equal to c to the power the degree of the extension. So this tells us that the number of number fields up to discriminant x would be about like a log x term away from the number of number fields of discriminant x and degree n. So let's define that quantity. Let us say nx denotes the number of k such that k over q is equal to n, and discriminant of k is less than x. Right? And so Linux, I think this is attributed to, but this is potentially Linux conjecture, uh, but I don't. It's a folklore conjecture, so it might be older. It says that there exists a constant Cn such that nx is expected to be about Cn times x. These are the expected asymptotics, and this is only known for very small values of n. So only known for n less equal 5. Right? In particular, n equal to 2 is a classical theorem. So n equal to 3 was done by Davenport and Heilbronn. N equal to 4 was a recent case handled by Bhargava. Not that recent, but still recent. And N equal to 5 was also handled by Bhargava. And there is no progress on this conjecture for any n greater equal 6. So there are two main issues that come up when trying to approach Linux conjecture. Uh, uh, the two main issues being, one is the issue of parametrization. Parametrization of rings. And I should maybe call it perfect parametrization of rings. I'll explain what that means in a moment. And the second issue that comes up is the sieve theoretic. Right? So what I mean by perfect parametrization of rings is you have sort of very nice theorems that characterize rings. For example, all quadratic rings are of the form Z of alpha, where alpha is an algebraic integer. All quadratics are isomorphic to Z of x mod x square minus t, or Z of x mod x square minus x plus t, where here you'd have to take d is congruent to 1, d is congruent, here no condition, here d is congruent to 1 mod 4. No, actually, no condition. These are the only forms of rings possible, called quadratic rings. And basically, it is every quadratic rings are uniquely isomorphic to one of these two forms. This means that basically to count the quadratic rings, we can only count these types of polynomials, and counting these types of polynomials will allow us to count rings. And to actually count number fields, we have to sieve out these polynomials for basically those polynomials that do correspond to maximal rings of integers. So we would, so basically this is the perfect parameterization issue at n equal to 2, and the sieving issue is basically determined by the fact that x square minus d corresponds to a ring of integers of a number field if and only if d is square free. And similarly, you have a condition of, I think, 4d minus 1 to be 4d plus 1 to be square free in this case. So basically, you have to sieve out those d's for which the d's itself is square free. Now, this issue is quite simply handled in this case. However, it gets a little bit more complicated for larger cases. So in an n equal to 3 case, the perfect parameterization issue is actually handled by uh, Levi Levi's theorem, a theorem attributed to Levi in Delon Fadi's famous book, Irrationalities of Degree 3. And what they say is every ring of rank 3 can be associated to a cubic binary form this association is unique up to the natural action or the twisted natural action of GL2 on binary cubic forms. So if you want, you can imagine it more directly. What they are essentially saying is every in algebraic geometry terms, what they're essentially saying is every rank 3 ring can be uniquely written as R is isomorphic to, or rather I should say spec R is isomorphic to proj of z of x comma y modded by f of x comma y for sub-binary cubic form and up to a unique action on variables. A direct way to imagine this is basically for if this particular association, if f of x comma y is a naught x cubed plus a1 x square y plus a2 xy squared plus a3 y cubed. Let's take a naught not equal to 0 so that we don't have to worry about certain things. The definition works in general. This above definition works in general. So if you take a naught not equal to 0, you can describe this rings as follows. You consider the ring RF given by the basis 1 a naught delta square plus a1 delta. So the Z span here is Z span of these three elements. And yeah, this is where delta is the image of x in q of x modded by f of x comma 1. Basically, if you consider the corresponding number field, right, then if f of x is irreducible, f of x comma y is irreducible, then this will be the corresponding number field, and you are just taking the root of f in that particular number field, and you're writing this as 1 a naught delta square plus a1 delta. This turns out to be a ring, and sort of this association is sort of crucial to Davenport and Heilbronn's theorem, where they sieve out binary forms which don't correspond to number fields. So Davenport and Heilbronn's contribution is sieving for f binary cubic such that RF is okay for some k. And n equal to 4 and 5 were both handled by Bhargava. Both the sieving and the parametrization side was handled by Bhargava. So if you remember right, n equal to 4, Bhargava says that quartic rings are in a one-to-one correspondence with a natural GL2 cross GL3 orbits of pairs of ternary quadratic forms. In fact, if you want to imagine this particular correspondence in the same way as this one, what you can do is you can say that this correspondence is basically given by, if you have two quadratic binary forms, ternary quadratic forms, f comma g, you basically consider f comma g to be associated to, sorry, f comma g is associated to the ring corresponding to the ring of the ring of functions of, I should maybe say R is the ring of functions of this. So ring of functions of z of x comma y comma z modded out by the ideal generated by f and g. So the GL2 action is basically the natural action of GL2 on f comma g, where basically A, B, C, D acts on f comma g by AF plus BG and CF plus DG. This is the GL2 action. And the GL3 action is the action on the variables. So you basically f comma g action by if sigma is in GL3, then the action by sigma is taking f to f of sigma of x comma y comma z comma g of sigma of x comma y comma z. Similarly, you sieve out the corresponding elements, which is not too hard in these cases, but it does require some work. So these are the sort of two main obstructions when it comes to trying to get to the bigger, higher value theorems, trying to get to Linux conjecture. For n greater equal 6, the biggest obstruction I would argue is the lack of a perfect parametrization theorem. You cannot sort of begin to think about this question without having some sort of a way to parameterize rings in a very concrete fashion. And so we talk about, the next thing to do is talk about the lower bounds for this particular quantity. And the history of the lower bounds is as follows. So lower bounds on nxn. And so we have Male in 2006, who showed that nxn is actually greater than x to the 1 over n. Then we have the famous Akshay Venkatesh and Jordan Ellenberg's paper. And Jordan Ellenberg, who showed that nx is greater than x to the half plus 1 over n squared. And then we have, this was I think in 2011, if I'm not mistaken. No, sorry, Male, this was 2006. Male was 2002. And so there was no progress for a while until Bhargava, Shankar, and Rai refined the particular argument to show this was in 2022. They showed that nnx is greater than x to the half plus 1 over n. Right? And then there is a paper that is still on archive where the same authors show that nnx is greater than x to the half plus 1 over n minus 1. And we basically show a small improvement of this. We are able to show nx is greater than x to the half plus 1 over n minus 1 plus 1 over 5 n to the 4 plus something small for n odd, and x to the half plus 1 over n minus 1 plus 1 over 88 n to the 9 plus some plus terms of higher order for n even. So we make a small improvement on the previous result. And yeah, so the obstruction, the two main obstructions in trying to get a perfect to try to approach Linux conjecture sort of can be divided into three problems when it comes to getting lower bounds. So the two obstructions turn into three problems, and I'll discuss them as follows. The first one is again always parametrization of rings. So the first problem is always good parameterizations. So in fact, all these first three theorems, all of these use the same parameterization, and this is the parameterization given by monogenic rings. So monogenic rings are basically rings. So a reminder, use so a monogenic ring is a ring of the form isomorphic to z of alpha, where alpha is an algebraic integer. So whenever you have a monogenic ring, you have a corresponding minimal monic polynomial associated to it, and therefore you can somehow work out how to. Therefore, you have some sort of a concrete objects to talk about those rings with. Right? So basically, what this ends up meaning is you have a natural map from you have a natural monogenic natural map from monic polynomials to monogenic rings. This map is clearly discriminant preserving. This is because the monogenic ring Z of alpha has the basis given by just one alpha, so on till alpha to the n minus 1. Right? So the discriminant of this particular ring will be the same as the discriminant of the corresponding polynomial. Right? So you have a nice discriminant preserving map, and you have the understanding that f of x and f of x plus n um, correspond to the same ring. And you have the third understanding that you can sort of 100% of monic polynomials when ordered by height when by height correspond to distinct rings. So this particular result, the third result, is based on this third fact and appropriate sieving of translation orbits to count rings which are maximal. Most of the work is about basically the sieving issue. This is there's actually a much stronger result than this given by Bursis, Giori, and Everest, which says that the number of monogenic presentations of a particular ring is finite. It's bounded by the degree. The bound they get is something like 2 to the 2 to the n square or something. It is humongous, but it is still completely bounded by the degree and independent of the discriminant of the ring. So this result is based upon this understanding. Actually, so is this result, though they do not have this particular part and they do not have the appropriate sieving material. Though the way they got this particular lower bound, Akshay Venkatesh and Jordan Allenberg, is they actually showed that the weighted lower bound of x to the half plus 1 over n. And they were able to use the upper bound that they got to get a lower bound. By showing that only so many of them will correspond to different things. So basically, from here to here, the major distance crossed was basically very refined sieving. Okay. And so let's talk about this result. The thing is, monogenic rings and monogenic number fields cannot give you a better result than x to the half plus 1 over n. So you have to somehow be able to, so the information, so obviously different polynomials, whether they're monic or otherwise, give you also every possible number fields. However, the information about the polynomial corresponds to the information of a direct ring. In this case, let's say z of alpha. And so the information of the number field or the discriminant of the number field is hidden within first the discriminant of the ring, which we have a good handle on, and the index of the ring in the corresponding number field, which is sort of determined locally. And that is where we do not have a good handle on it. And therefore you cannot get a very good lower bound. So this particular result, this particular result uses a more general parametrization known as binary rings. So this you can see, the monogenic rings is basically the parametrization of quadratic rings. And basically binary rings, this second result is based on the corresponding parametrization of cubic rings. So binary rings. Okay. So let's take a binary form f of x comma y.
Gaurav, can I ask you a basic question? So if you just look at the monic polynomials, would you get all, so the parametrization that you have, would you get all the fields or no? The issue is that you're going to be missing some fields.
You will get all fields. Getting fields is not an issue because you can always find a primitive element in a number field,
Okay.
right? The moment you have a primitive element, you can just multiply by an appropriate integer to make it integral, and you will always get the all number fields.
Okay, so
The problem is if you sort of look at how they're distributed, they will be distributed. So if you have, let's say, if you imagine in a two-dimensional sense, they will mostly be distributed along the cusps. right? If you consider the space of all polynomials with discriminant less than x, that particular space will have cusps. And basically, most of the number fields will be distributed in the cusps. And those number fields, basically, the discriminant of the ring that you're getting, which is bounded above by x, the discriminant of the corresponding number field can be much smaller than the ring. And that information is sort of in the index of the ring in the number field. And that information in terms of the polynomial is available to us locally. And even then it requires modulo like p to the n calculation. So I think it can be reduced to modulo maybe some p to the n by 2, but that is a different question. But basically, we do our handle on the local on how what is the index of the ring in the number field is a local information, and that varies a lot. There's no universal way to compute it, and basically you want yeah.
So if to get all the fields, you would have to, yes, if you consider all, if you let your if you consider all discriminants this way, you do get all the fields. But once you bound your discriminant, then you're going to be missing some fields.
No, even if you bound your discriminant, you will get all the number fields with discriminant less equal x.
Okay.
But the thing is that number field with much smaller discriminant will correspond to rings which are in the cusps, and basically the cusps are hard to count. So instead of, if you look at it in terms of height, if you look at polynomials with the heights h, then the number then even if you then if you take a large enough height, you will sort of get polynomials of you'll sort of get all number fields, but the height of the polynomial that you'll have to go to will be much larger than x itself. And even then, you will have to extract the local information for every ring, and the local information is not like sieving. It is uh, it is not like sieving. It is more in the form of more like in the tail end form of the usual sieving. Does it make sense?
Yeah, I think
This
so.
will make more sense in a moment. Okay.
Gaurav, perhaps what happens if you are fixing index? Can you make the estimation?
No, that's the thing, because index information is available to us locally.
Yeah, but suppose that you would assume that you have given
So it takes, so for example, one of this particular jump from the improvement that we are able to make comes from the fact that we look at something along the lines of we handle index by saying that look at all number fields whose index is divisible by m. That kind of information is quantifiable. But index equal to m becomes very hard to quantify. You will have to do annoying sieving along that line, and as it is, the objects are moving around a lot.
Thank you. Yeah, that's good.
Okay. So if you have a binary form a0 x to the n plus a1 x to the n minus 1 y plus so on a and y to the n, and let's say for the sake of argument irreducible, this can be done, all of this works without this assumption, but things are much easier to talk about. Let kf denote the field z of x mod q of x modded by f of x comma 1, right? And let delta denote the image of x. Right? Then Rf is defined to be the z span of 1 a naught delta square plus a1 delta a naught delta cube plus a1 delta squared plus a2 delta, and so on until a naught delta to the n minus 1 plus a1 delta to the n minus 2, and so on until a n minus 2 delta. And so I think this is might be older, but it's attributed to Nakagawa. It is a classical result that says that RF is a ring. So because RF is a ring, what ends up happening is this RF is a ring, and one can easily see that the discriminant of RF will be just discriminant of RF, because you have basis can be seen as A naught to the 2n minus 2 times discriminant of delta, which is just the discriminant of the binary form by definition. So again, you have this nice discriminant preserving map from binary forms of degree n to binary rings. Discriminant preserving map. So what do you know about this map? We know that RF is actually equal to R of F of sigma for sigma in GL2. That is, this particular ring is invariant of the natural GL2 action on binary forms. Right? And you know that you can find a cone in which all polynomials, all binary forms correspond to distinct rings. So Bhargava Shankar Wang's 2022 result, the archive result, is based on this fact and sieving out binary forms that do not correspond to rings of integers. So that this particular result, 2022 result, is based upon basically these two facts. Again, there's a versus Everest and Giori alternative for this particular result. That says that the number of binary presentations of a given ring is totally bounded by the degree. So, yeah. Okay. So we come to our again as it turns out, this is expected to be the best possible result one can get using the parametrization of binary rings. And so we need more general parametrizations to be able to get even better lower bounds. Right? So basically what ends up happening is monogenic, while number fields can be reached using the monic polynomial, the ring of integers cannot be reached using using monogenic rings, right? So you sort of need a parameterization that captures more and more rings. Binary rings capture more rings than monogenic rings. One can see that whenever A naught is 1, this is basically a monogenic ring. So So I'll define the concept of weakly divisible polynomial, which was defined in their papers. So a weakly divisible polynomial is a polynomial of the form, oh sorry, I'll say this way. A polynomial f is said to be weakly divisible by m at L if m square divides f of L and m divides f prime of L. Okay. So basically, if you consider f of x plus L, or equivalently f of x plus L, will look like something like b naught x to the n plus b1 x to the n minus 1, and so on. M square bn plus m bn minus 1x plus m square bn. So this is how the polynomial will look. In both of these papers, these polynomials are sort of the major hindrance. These types of polynomials are polynomials that do not correspond to the rings of integers of number fields. And they are the major hindrance in sieving because these types of polynomials are not easily sieved out by the Ekedal sieve. So what the Ekedal sieve does is Ekedal sieve allows us to, in any sort of a robust space. So Ekedal sieve, what it allows us to do is in any robust space. By robust space, I mean that its surface area is small with respect to its volume as the space expands. So in any robust space, if you have V variety of codimension 2, or more, and you want to know points P in the robust space, I should say, I'll use P in the robust space, such that P mod P is not in V of Fp for all P, primes. So if you want to know this particular number, Ekedal sieve will allow you to say that this number is actually equal to the volume of the R space-time constant. Constant Cn, that C space. This particular constant is just determined locally by the local proportions. Actually, what the Ekedal sieve does is it actually gives you a nice bound for this, which is sort of the tail end of this, P in R space, so that there exists P greater than M, so that P mod P belongs to V of Fp. So it actually allows you to say that this is this number is about the order of the volume of the R space divided by, I think, the surface area, sorry, something of the order of the surface area times the volume over M. So something of that sort. So it allows you to give an upper bound for this quantity. As a result, you are able to show this particular result. And these types of polynomials are sort of the only polynomials that cannot be easily sieved out using this particular setup, the decadal sieve setup.
Go ahead. In the second, in the last line, you mean P mod P which do not belong to or belong? Yeah.
Or belong to. So you want so
belong. Okay.
Yeah. So this is this will, if you decide to sieve this sieve the robust space for these types of elements, then this will be the tail end.
I see.
So actually, decadal sieve allows you to bound the tail end, and therefore it implies this. Okay.
And V is contained in the robust space? Is the subvariety of codimension 2 of the robust space? Is that?
Yeah. Well, subvariety is, when I'm looking at robust space, I'm sort of looking like Z to the N or something. And you're looking at a variety in Z to the N.
I see.
So it need not be inside the robust space, but basically there exists some part of it that will be in the robust space.
So it all sits in some larger ambient space.
Yes. Okay. So yeah, so as it turns out, these are the only types of polynomials that are not easily sieved out by the decadal sieve and don't correspond to maximal rings of integers. These are polynomials that absolutely do not correspond to rings of integers, the corresponding rings, and therefore sort of sieving these types of polynomials out was sort of the major achievement of the previous two papers. And what we do is we ask a different question. Okay, so this does not correspond to the ring of integers. Then does it correspond? Can you somehow extract a larger ring inside this that contains this ring, right? So here is our theorem that allows us to get the first improvement that we talked about. This is a parameterization we call weakly divisible rings. And what this says is if f is a binary form or polynomial is weakly divisible by m at 0, and f is equal to, let f be as before, then r prime of f comma m, r prime of f comma m, we define it to be z of 1 comma e naught delta. This very same basis except for the last term, which we divide by m. So if you look at this particular RF, we show that r prime f comma m is a ring when f is weakly divisible by m at 0. So this ring, discriminant of this particular ring, will exactly be discriminant of f divided by m squared. Right? So basically, if you're looking at rings of discriminant less than x, then you can, provided you only look at weakly divisible polynomials, you can look at polynomials with much larger height to capture rings of discriminant, number fields of discriminant less than x. Right? And so this particular parametrization, so we don't exactly do a lot of work with the sieve. What in this particular previous paper, in proving this particular bound, they actually give a power saving term in their particular tail end sieve, And because of that power saving, we are able to squeeze a slight improvement using this particular parametrization. And we are able to show that nx called nx is greater than x to the half plus 1 over n minus 1 plus something small n odd and greater than x to the half plus 1 over n minus 1 plus 1 over 88 n to the 9 plus dot dot dot. So in terms of instead of counting number fields, we can also count rings to get an idea of how good this particular parameterization is. And to that end, we show that the number of rings of discriminant less than x is greater than x to the half plus 1 over n minus 4 by 3. So in fact, we have another result that I don't think I will get into today. That actually shows that the lim sup, we develop a slightly different sieving technique of n goes to infinity of n and x divided by x the half plus 1 over n minus 4 by 3 minus epsilon is always infinity. So in a sense, we show that the limit, the lower bound is true for infinitely many values of x. And so this is the reason why we get only this particular lower bound is we fail at this particular this is the point at which injectivity, the method of injectivity that we use stops failing, right? So like here you get 100% of the polynomials of a distinct of a specific type of polynomial correspond to distinct rings. Similarly, you have a cone in binary rings, you have a cone in which all the polynomials correspond to distinct rings. That sort of stops failing, but assuming that does not fail, then we potentially could go as high as x to the half plus 1 over n minus 5 over 3. But this is sort of the limit. We do not expect it to be better than half plus 1 over n minus 2. That is sort of, so we still need better parameterizations of rings.
Sir.